Okay, good morning. I'm very happy to be reporting on something completely different, namely on the highlights of the heavy ion experiments, which is a large community, and those are the experiments where I've taken results from, or where I've been given some of the results, and I would like to thank all the contributors to this talk very much. Now, what I'll walk you through is how we actually characterize the medium that we create when we bombard large nuclei, and what this actually means when we talk about the conditions at which these collisions cease, when they freeze out, how they evolve to that final state, what the special role of heavy flavors in this is, and how they actually melt and regenerate, how their energy loss is characterized, how in general the matter actually behaves with regard to transport coefficients in the medium, and then a little outlook on the recently measured Electroweak probes and how they are related to nuclear parton distribution functions, and some exotic results if I have time left. Now, what we try to do is we try to actually link the global properties or bulk properties depicted in this phase diagram down here, where we start with cold nuclear matter, and through bombarding these nuclei actually move into the quark-gluon plasma phase, and I hope I can show you the evidence that we have that we reach this phase, and then how eventually the system cools down and hadronizes again. So we start out with an initial state, and we have hard scatterings, and the system thermalizes in some fashion until it reaches chemical freeze-out, at which all the final state particles are actually have been produced, and there are no inelastic collisions ongoing. And then the system further evolves until a state is reached, which we call kinetic freeze-out, at which point the momentum distributions are frozen out. Now, in a sense, what we try to do is we try to see how this evolution of the phase transition back into normal matter, much like in the Big Bang, actually proceeds in each and every nucleus-nucleus collisions, with a minute difference that in the Big Bang this took about 10 microseconds, and the baryon fraction was only 10 to the minus 10, and here this is done in 4 times 10 to the minus 23 seconds, and the baryon fraction is about 10%. Now, what evidence do we have that we need the conditions to actually produce the plasma? And one of them is, are you above the critical temperature, which is predicted by lattice QCD? That is around 160 MeV. And definitely we think we are. This is actually the evidence that we have. We measured direct photons that come out of these collisions in central lead-lead collisions, or gold-gold collisions, because these are data both from the RIC experiments and from the LHC. And what you actually see is that while out at high PT, you have a perfect description of the photon spectrum from perturbative QCD, there's a significant enhancement above that at very low PT. And since all of the resonance decays and stuff have been subtracted, so these are really direct photons, we believe this can be interpreted as thermal radiation. And what you can then do is you can try and fit this, and when you do it, you actually see that at RIC you reach temperatures of 220, or an inverse slope parameter. At the LHC, actually something like above 300 MeV. This is definitely above the transition temperature predicted in lattice QCD, and actually it shows that the slope goes up when you go to higher energy, and also the invariant yield, which is shown in this inset, is going up. Now, as the system evolves, you freeze in, and your particle ratios are fixed at a certain point, and you can ask a simple question: what does it take to create these observed particle ratios? So you can apply some statistical model, and if you do that, you actually find that the best description of the spectrum, the measured spectrum, which involves all kinds of final state particles up to heavier nuclei actually, is best described if you assume that this chemical freeze-out happens at 156 MeV and a vanishing baryochemical potential. So this actually is also at the phase transition. Now, the system then further evolves, and if you consider central collisions, there's a huge pressure buildup. Lots of particles are being produced, and this pressure drives the system outward. And of course, depending on the mass, the pressure is common to all of the particles. And then depending on the mass of the particle, this is for pions, kaons, and protons, actually the shape of these final state distributions changes. And if you make a simple assumption, namely what would you need to describe such an explosion in terms of a common thermal velocity and an expansion on top of it, a thermal motion and a common expansion velocity on top of it, you actually find that this is going outward with a significant common velocity, 2/3 of the speed of light, and the kinetic freeze-out temperature at that time is then, of course, since the system has further cooled down, below that, what you measure in the chemical freeze-out. Now, in non-central collisions, you can actually see how this pressure evolves, because what you start out with is you have a reaction plane where you have the two nuclei colliding. You form this almond-shaped region, which represents a spatial asymmetry. And that spatial asymmetry, through the internal pressure, actually develops in a momentum anisotropy. And this anisotropy you can quantify by doing a Fourier expansion, if you like. This is only showing the first term here, which we call the elliptic flow, so the ratio of these momentum distributions. And if you study these for all kinds of produced particles, what you actually see is there's a very large elliptic flow, which is consistent, and Charles Gale will allude to this later on, with a strongly coupled medium with low shear viscosity expanding. And if you look at this for all kinds of identified particles, you see what we call a characteristic mass ordering. The shape of these curves, the evolution of this elliptic flow with the particle transverse momentum, has a characteristic mass dependence. And it was thought that this actually has to do with whether the particles are made up of 2 or 3 quarks, and there was a scaling introduced at RIC where if you scaled these, the PT with the number of constituent quarks and the elliptic flow with the number of constituent quarks, you would find a unique description. Now that is no longer holding at the LHC. Clearly these curves are not all on top of each other. Indeed, mass is what seems to be driving this effect. And here's a recent example of what we measure in the elliptic flow. And if we compare, for example, the phi meson to the pion and the proton, it really behaves more like a proton, which has roughly the same mass. Now the question is, there's more to it than just elliptic flow. There are higher orders of moments in there, and it's not straightforward to really see why there should be odd harmonics. And actually, as Charles will also explain to you, these odd harmonics are very important because they're present in the initial state, and the question is, how are these initial fluctuations that you have, because you don't have perfect shapes, you have overlaps of lots of nucleons made of partons. And the question is, how do these actually wash out? And there is a strong sensitivity to the washing out of these resonances, depending on what viscosity, for example, you assume to be present in the system. And one of the striking features is, if you look, for example, as a function of centrality from the central collisions to the most peripheral collisions, at the third harmonic there, if you like a triangular flow, you actually see that it doesn't change much. So this is a strong indication that this is mostly driven by initial state fluctuations. So this is a way that we can actually get a handle on these initial state fluctuations, which otherwise are very difficult to describe. If you move on to extremely central lead-lead collisions, and you make a stringent analysis of all these moments up to the 7th moment, this has been done by by CMS here, then you actually see that as you go to the most central collisions, this I think is 0.2% centrality, the red dots here, they all level off. So in all of these moments, actually, there is an imprint remaining which comes from the initial state. And this is something, again, that one needs to quantify now in a sort of model-guided way. Another way of looking at it is, the question is, if all of these moments are present in the system, how do they actually relate to one another when you go from peripheral to central collisions? So what's plotted here is the elliptic flow on the x-axis, and then with respect to that, either the same in a different momentum range or higher moments like the V3, the V4, the V5. And you see there's this kind of characteristic, certainly non-monotonic boomerang shape. And this is actually consistent with hydrodynamic predictions which actually have a strong damping, and this will be further explained in the talk by Charles. Now, particle correlations. This is a picture that at least some of you may have seen. If you correlate just the angles of measured particles, you pick out one particle, one with a particularly high PT, for example, and you correlate all other particles to it within the delta eta, delta phi space, then you see this kind of a jet peak and then something on the other side. But what you also see is that there are these ridges developing in delta eta. So there are long-range correlations, and they are present both in high multiplicity PP systems as well as in lead-lead systems. And most recently, they've also been seen in proton lead systems. Now, how can one quantify what's happening underneath this peak? Well, you subtract your high multiplicity structure, your low multiplicity structure from your high multiplicity structure, so all the correlations with respect to the one particle sticking out are gone, and what you're left is what the underlying event has a shape in terms of, for example, the Fourier components that you can now extract from this angular distribution. And if you do that, again, and actually quite as a surprise, you see the characteristic mass ordering if you look at the type of particles being emitted from there. You get more or less the same mass scaling as observed in the elliptic flow in lead-lead collisions. And moreover, if you don't look at single particle elliptic flow, but if you really calculate these with cumulants of 4, 6, and 8 particles, you actually see that as you go from lead-lead to proton-lead, these modes stay very large. This is a very strong indication that there's really true collectivity, because all non-flow components are effectively erased if you go to these cumulants, and they stay large, even in proton-lead. So I think by now you should have sort of grasped that the system has a strong interaction. It quickly equilibrates, and it produces this large flow. And I need to move on. And the energy loss, if we now look at particular ways of how particles lose energy in the system, one way of characterizing it is you compare the measured yield in lead-lead collisions and you compare it to what you find in PP collisions, appropriately scaled to the number of underlying collisions. And what's been found is that you have a strong suppression with regard to different particles, which is usually coined jet suppression. Now, with heavy flavor energy loss, we're looking at Ds, for example, and we can quantitatively now verify that also the Ds are very strongly suppressed, and we get some constraints on the models describing this, and most interestingly, we see that actually as we go from Ds to Bs, the suppression changes, so we see the first sign of a quark mass dependence where the Bs are less affected than the Ds. Again, there's elliptic flow even in these D mesons, and that gives us the chance of actually also studying the RAA, now looking at whether the particles are emitted along the long axis of this ellipsoid or across, and actually we see a difference, and this again gives us a handle on actually quantitatively describing this energy loss. This has also been measured at RIC, actually in gold-gold and uranium-uranium collisions, and there actually one finds that the yields are very similar, and the suppression pattern is very much like it has been observed for the light flavors. There's also been a description of the system size dependence there, and if one looks at heavy flavors from electrons, actually one sees that as you go from a very small system, there seems to be an apparent enhancement. As you increase the system size, actually you come to this characteristic suppression pattern, and that still needs to be explained. Quarkonia, there's an old paper by Matsui and Zatz, which actually said that one of the characteristics is that you have the melting of quarkonia in the medium, And then as you produce, this is this description through color screening, but then if you produce lots of these J psis, for example, you have a certain chance of regeneration, and then there should be a energy dependence. And now what's shown here is a description of such a regeneration model compared to the RIC data and a prediction for what this should look like when you go to the LHC. And actually, this is what is being observed. So you have, in general, you see the melting of the states. So this is PP. You see, for example, here all the J psi states, and then you see the strong, the upsilon states, and here you see the strong suppression in lead-lead collisions. But this is the characteristic change with energy that I was alluding to, where the J psi here has this downward trend in the RAA, and it stays up at the LHC. And this is a strong indication that we actually have a regeneration at play there. This has also been measured in P-lead, and I should say that if you look at the RP-lead, the theory, you need a theory involving energy loss in the cold nuclear matter and some shadowing to really describe this well. You have a stronger suppression at low PT, and I think it's already evident that it's difficult there for the models to get the rapidity and PT dependence correct at the same time. LHCb has also measured this for bottom. For bottom, actually, here the upsilons, the effect is much smaller again. This is the J psi point, this is the upsilon point. Still, of course, dominated by statistical uncertainties. Now, how are jets modified? If I have a hard collision going on in PP, it fragments into the vacuum. In AA, again, it is suppressed. And if we look at, for example, reconstructed charge jets, here a ratio of central to peripheral collisions, which are sort of also testing the suppression pattern, and actually across the entire energy scale, you see that between the various experiments and the way of reconstructing these jets, you get very nice agreement between them. So the leading jet particles are just as suppressed as you have the whole jet suppression. This is beautifully exemplified in this plot where you study photon-jet correlations, where you actually measure the fraction of what is contained in the jet on the side opposed to the measured photon. So you tag the photon, and as you go from peripheral to central collisions, you actually see in peripheral collisions you have essentially the shape that you would expect also in PP collisions. As you increase the centrality, actually you have a strong suppression on the opposite side. So you get a smaller energy fraction in the jet and also a total reduction in the integral. So they are really efficiently quenched away. And CMS has looked into this in great detail, how the energy is actually being redistributed. So you start out with a jet more than 120 GeV, and you find that there's 35 GeV missing on the opposite side. And then you see how this is actually redistributed as a function of the PT of the particles produced, and you actually see that this is mostly coming out as very soft particles on the other side. There's a nice measurement by Atlas, which shows that actually if you look at this jet RAA, now this is the rapidity plus minus 2 folded onto each other, and you actually see that the suppression pattern for the different centrality classes remains essentially constant. So the medium there, this is a non-trivial effect, and the medium actually seems to look identical over a very large extent. This is non-trivial. In proton-lead collisions, if we compare proton-lead, lead-lead, and central lead-lead, you actually see that, for example, the fraction of photons within associated jets essentially looks like PP. So in P-lead, it seems as though there's very little quenching. In detail, there is something which is still to be understood, namely if you select different centralities, you actually find that some of the jets are enhanced in peripheral collisions and they are suppressed in central collisions. And the origin of this centrality depends, still not clear. Electroweak bosons, there are some beautiful results. These are really kind of standard candles now for things that we can scale, for example, PQCD calculations to, and we see that if we look at lead-lead collisions, the RAA, the nuclear modification of what you expect for your electroweak gauge bosons, they're the W and Z, and in yellow actually the photons that you have, this is essentially 1. This is the way that you would expect things to proceed, and it actually tells you that you're calculating the number of collisions to which you normalize your distributions to correctly. So from this, there's a nice measurement that came out which shows the Z boson distribution. The spectral shape essentially stays identical as a function of the centrality, which it should if it scales just with the number of hard collisions. And so in essence what we find, which is also shown nicely here, that is very consistent with Pythia simulations. The Z's have been measured in P-lead as well. There may be a slight forward-backward asymmetry here. If you look at the magnitude of, if you fold the spectra and you look at the forward-backward ratios, there's a slight decrease here, and models are now challenged to really describe this correctly, and also, of course, the statistical error bars need to be reduced. W plus and minus measurement, now here from CMS. This is essentially following what we find predicted. If you look at the charge asymmetry measurement, then actually you see that in the lead-going side, there is a deviation from what you would expect. And since this is a charge asymmetry there, this could actually hint to a different treatment that is needed for the up and down quark description in the parton distribution functions. So second but last, there's also a completely different way of going about physics in heavy ion collisions, namely not to collide them. If you don't collide your heavy ions, they are highly Lorentz contracted, highly charged ions, and they have a huge photon flux. And this photon flux can be very efficiently used to do photoproduction. And several measurements have actually come out. And one of the more recent ones are, for example, a first measurement of the psi prime. And the psi prime going either into 2 leptons or into 2 leptons and 2 pions. This is actually showing one of such events where nothing is happening except the exclusive production from a decay of such a psi prime state. And this is actually putting very strong model constraints. This still has a huge statistical error bar, but if you look at the range of model predictions of what has been affected, one can say that already strong shadowing is disfavored, and there have to be nuclear effects. So if they are not there, then we don't get a correct description of the measured yield. And last but not least is a result which is not putting any limits to things that we normally measure, but to something that other people measure. Namely, there has been the question whether dark photons, for example, photons of a certain mass that decay into E plus E minus, could be a possible explanation to the still existing G minus 2 result beyond the standard model. And so there are theories out there that say that they should have a low mass below 1 GeV. They should have weak coupling, of course, and they should have a very narrow width. And if you can measure your dilepton spectrum, then you can actually search for these, and you can also look what the total yield is that you find. And so the lines here indicate the limits by the G minus 2 experiment, 2 sigma, 3 sigma difference, and these are sort of the upper limits that have been measured by the Phoenix experiment on the existence of this final state with such a U particle in there, and actually also by an experiment which was carried out at GSI. So since this is double logarithmic, these lines now show up as straight lines, and you can actually see that they are nice exclusion, or not quite full exclusions yet, but they are putting a stringent limit to the interpretation there. So since no photon is observed, it is almost sure that the dark photon there is ruled out as an explanation. And finally, I think, or I hope I could convince you that this field of hot and dense QCD matter, as we call it, you may also call it quark-gluon plasma, because I'm convinced that this is what we are talking about, is really entering a new era of precision measurements. And we will have high statistics at the LHC in all of the collision systems that we look at. We will, in run 2, likely get almost an order of magnitude more statistics. Then we have the pending beam energy scan at RIC, which aims at really looking at details of the phase diagram, in particular a point which I didn't allude to, namely whether there's a critical point in this phase diagram. And all of that should help us pin down the initial condition, how they evolve through relativistic viscous hydrodynamics with the viscosity over entropy ratios, sensitivity there. Then a quantitative determination of the energy loss of the various flavors that we have at hand from the first hard collisions and how they evolve. And last but not least, from these proton-lead collisions, also a determination of nuclear PDFs. And all of this, since this is a plethora of experimentally driven observables, this needs the tremendous advance in theory, which will be presented by Charles, to really come to quantitative statements on those things like the transport coefficients and the like. Thank you very much.
So we have time for a few questions. There's one back there.
Is there elliptic flow in PP at high multiplicity events?
So PP is very special. We see indications for flow even in, or especially in very central PP collisions, and this is a puzzle that, well, not a puzzle, it's a challenge how to really describe this properly. So in other words, at which system size actually does a proper hydrodynamic description of the system break down? And this is an ongoing debate, and it seems that you can actually go to very small system sizes because the parton densities are large enough that apparently you reach some kind of a phase that can be described by a hydrodynamic evolution.
There's one question in the back.
I'm still a little bit puzzled how you like to determine really nuclear PDFs, because even from our EA scattering experiments, we know the mysteries of the high Fermi motion region, which we never really understood, and nuclear shadowing, so strong onset of diffraction. And this is what you have in your nucleus, and even in the proton, we don't know very well. And then you have collective phenomena, as we just discussed in proton-proton.
Yes.
How do you like to distinguish that it is really then,
I think
let's say, a convincing
yes.
picture with high precision? So is it not more appropriate, really, to make independent measurements?
I think one can do independent measurements, but I think this is definitely giving a handle, because you can actually pin down some of the X ranges. You you cannot pick exactly the X that you would like to look at. You're completely right, but in scanning all of these, I think you will eventually get a better understanding of the nuclear PDFs as they are out now.
Yeah, but you still have to model your collective
It's
phenomena,
correct.
which may break down QCD factorization and which may spoil
All of
your
this needs to be looked at, sure.
Okay. There's another question there. The last question.
Has there been any theoretical understanding of the actual arrival at equilibrium? In other words, we start with the collision. Do we have a theory? Do we have any theoretical understanding of how we go from that initial collision to thermalization?
We do, and I think this is a large part of the talk to come by Charles. So we start with some plasma state, and that actually evolves through viscous hydrodynamics. What we don't have, and there's no good theoretical description, is how the phase transition to hadronization actually happens. This we don't, as far as I know, don't understand theoretically too well. But the expansion part, this is well understood now.
I'm not talking about the expansion. I'm talking about setting up a temperature to begin with, not about what happens after there's a temperature. I'm talking about the pre-temperature going from zero when they're colliding to some temperature after they're in this state you want to expand. Is there an understanding of how that happens?
I think not quantitative, no, but I think their guide, I mean, we need certain energy densities to produce the state that we have to actually drive this pressure so that you can put limits. We know what the integrated emission rate of the photon spectrum is. We know that this, of course, is radiated through the entire collision, but actually one needs to really unfold this now very carefully.
Okay, I think we should proceed. Let us thank the speaker.